Okay, so first of all, to find an inverse, you have to switch your x and your y around, or in this case, it's x and f of x. Sorry, oops. No, that's not what I wanted, maybe. Yeah. So the x becomes an f of x, but I am going to give it that little notation of inverse, that exponent of -1, and then it says +1 up there also. So that's step one, is to switch your x and f of x around. Step two is to now solve for your f of x. We're going to try to get this alone. So I'm going to subtract 1 from both sides. X minus 1 equals 1/4 times inverse f of x. Next step is to get rid of the 1/4. The easiest way to get rid of the 1/4 is to multiply by 4. To multiply this side by 4, distribute that. Now the f inverse is isolated, and it equals, when I distribute, 4x minus 4. Number 2, f of x becomes x becomes f inverse of x. But this time we have to square it. So I'm going to throw in parentheses and square it. And then it says minus 4. That's step 1. To switch the variables. Step 2, solve for f of x. So I would add 4 to both sides. And then one thing still to do to solve for f of x is to square root. If you square one side, you have to square both sides. If you square root, you need to remember the plus minus. So now on that right side, the square root and the square cancel out. So you're left with f inverse of x. I'm just switching my sides around. You don't have to do that, but then you have plus minus square root of x plus 4. You cannot simplify that because of the plus. If that was x times 4, I could square root 4, but it's not times 4. It's plus 4, so there's our answer. Number 3, to show that they're inverses, you have to get full credit, you have to plug one function into the other and show that everything cancels out except the x, and then go the other direction. So we're going to do f of g of x. That means you're plugging the g into the f. So the g of x is 5x minus 3. It's going to get plugged into the f function. So it goes into that numerator in place of the x. So 5x minus 3 plus 3 over 5. That numerator simplifies. The negative 3 and positive 3 cancel out. So you get 5x over 5. 5's cancel out. Whoops, I didn't mean to write x there. I meant to write an equal sign. Equals x. That's what we wanted. Good, I put a little check there. It worked. Then I have to check the other way. I'm going to switch colors for the other way. So now I plug the f into the g. So instead of 5 times x, it's going to say 5 times that fraction minus 3. Well, don't distribute that 5. The 5's cancel. You're multiplying by 5 and dividing by 5 at the same time. They cancel each other out. So now you're left with x plus 3 minus 3. Well, plus 3 minus 3 cancels out. You get x. Check, that worked as well. So I verified that they were inverses. Okay, to graph a square root, remember what the number inside the square root and the number after do in terms of our starting point. What is our starting point? -1 is the y. -3. You have to switch that value from inside. It said +3 in there. We switch it to -3. That's going to be the starting point. Remember, it's kind of like array. It doesn't have arrows on both sides. That side is the starting point. What would be the next x value that would be nice to plug in? Probably not 0, because 0 plus 3 is 3, and the square root of 3 is not a nice number. 6 would work. There's smaller numbers I could plug in. 4 would make a 7. That wouldn't work out nicely. 1 would work, but I actually skipped 1. So let me plug in the 1. Let's do that. 1 plus 3 is 4. Square root of 4 is 2. So I'm going to put 2 times 2, which is 4, minus 1 gives us 3. What other in between -3 and 1 would be a nice one to plug in? -1 plus 3 would be 2. Square root of 2, it doesn't work out nicely, but we're getting close. 0 plus 3 is 3. Square root of 3 doesn't work out nicely. How about a -2? What happens when you plug in -2 into the square root? You get square root of 1. And the square root of 1 we know. Square root of 1 is 1. So then we have 2 times 1, which is 2, minus 1 is 1. My goal is to take the square root of 0, take the square root of 1, and take the square root of 4, because those all work nicely. So I had to think about what x values I needed to make that happen. If I have x plus 3 and I want 0, I needed a -3. If I have x plus 3 and I want 1, I'd get a -2. If I have x plus 3 and I want a 4, x has to be a 1. So those would be good numbers to pick. They're not the only ones that work, but they are the smallest ones that work nicely. So graph them. Oops, that was not correct, sorry. -2, 1. Okay, then I have 1, 3. Put an arrow on the right side, but not on the left. So the domain. Domain is your x values. What's true about the x values? They had to be bigger or equal to the -3. Anything less than -3 gave us an imaginary number. Meanwhile, f of x, it got down to -1, and then it went up from there. So it had to be greater than or equal to -1. So those numbers, remember, they come from the h and the k in our function. Number 5, what x values should I use? I need to use 1. I would like to use 5, but I'd like one smaller than that as well. 1 minus 1 was 0. I already used 1. 3 minus 1 would be 2. Square root of 2 isn't nice. 5, I already got 5 on here. Remember, we got, I'm getting the 0 here. I'm going to be able to take square root of 0 because I'm plugging in 1. 1 minus 1. If I want to get 1, the square root of 1 works nicely, I need a 2 there. 2 minus 1 is 1. Okay, so then we plug them in. So 1 minus 1 is 0. Square root of 0 is 0. Minus 4, -4. Then plug in 2. 2 minus 1 is 1. Square root of 1 is 1. Minus 4 is -3. Plug in 5. 5 minus 1 is 4. Square root of 4 is 2. Minus 4 is -2. Domain. X had to be greater than or equal to 1. This problem didn't use f of x, it used y, so I'm going to stick with the letter y on my range. It was greater than or equal to -4. Then I get into the simplifying section. Simplifying square roots is probably a little bit more natural to you than some of the other roots. So number 6, we have a coefficient of 64, but then we also have n's and we have w's. You might want to think of each of those separately. So you're welcome, if you want to rewrite You can think of those all separately, that's fine. Square root of 64, does that work out nicely? Square root of n to the 6th, n to the 3rd. Square root of w to the 4th, w to the 2nd. I'm going to jump down to number 6 before I do number 7. Or sorry, I'm going to jump down to number 8 is what I meant to say. 8 is a square root also. Number 7 is a 4th root, so I think 7 is a little trickier. So look at 8. You can break them apart again. And I have the square root of 45. 45 is not a perfect square. So the square root, if you plug it in the calculator, you're going to get an ugly decimal. And we don't want ugly decimals. We want exact answers. Not even the calculator rounds it because it's irrational. You cannot express it exactly as a decimal. It's not physically possible. So we've simplified square roots before. Do you recognize a factor of 45 that is a perfect square? 9, yeah. So I would break that. Oops. I don't know what it was here. I meant to write a 9 there. Here, I'll erase and try it again. 9 times 5. Okay. I would break it apart like that. So the square root of 9 is 3. The 5 doesn't get to come out of the square root. It's stuck inside the square root. Notice I left a little bit of space for my variables. Now look at the x's. Square root of x to the 3rd, does that come out nicely? No, because 3 is an odd number. So if you wanted to break that down, you can. You can think of it as the square root of x squared times the square root of x. Then you have an even number and then the odd one left over. What's the square root of x squared? X. We got to pull x out once, but then that other one is left on the inside with that 5. What about y to the 8th? That's an even exponent, so that works out nicely. It becomes y to the 4th, and there are no leftover, no remainder y's. Now let's jump over to number 7. Number 7, so we can break apart. I'm going to give myself a little bit of room. I'm going to break it apart up a little bit higher. So you can separate each of the things, that's fine. But the 4th root of 48, you're not probably as good at 4th roots as you are square roots. You haven't done them nearly as often. So if you think about what we just did with the 45 on number 8, we broke 45 into a number that worked nicely and then kind of the remainder. We have to do the same thing with 48. We can't do the 4th root of 48, not exactly. But maybe there's a number that can be divided out of 48 that does work nicely. So it's helpful to know some perfect fourth powers, I think. And maybe you don't know them, but we can make a little chart off to the side. So let's think of some fourth powers. 1 to the 4th is just 1. That doesn't really help us. Let's skip 1. Let's think about 2 to the 4th. 2 to the 5th is 32. So 2 to the 4th is 16. Let's keep going. Let's do a few more. 3 to the 4th. Anybody know that one? That's 3 to the 3rd. Oh. How about 9 times 9? 81. So 4 to the 4th, 64 is 4 to the 3rd. So 4 to the 4th, you could think of it as 16 times 16, 256. Okay, and they get large very quickly. You can see that. By the time I get to the 5 to the 4th, I'm already in 4 digits. So I'm going to stop my list right there. I don't think there's any use in going further. But other than 1, 16, 81, and 256 are the smallest perfect fourth powers. Can you take any of those out of 48? The 16, 48 is divisible by 16. How many times? Let's do this a little. Let's do it down below. So you can break 48 into 16 times 3. Look at the V's. Do I need to break V's down, or is that going to work out nicely? That one works out great. What about the Z's? Is 13 divisible by 4? No, so let's break it apart. What can I use? 4 goes into 12, right? And so how many Z's will I have remaining? 1. There'll be 1 Z left over. Notice all of these are still 4th roots. That doesn't change. But some of these can simplify. I'm going to circle the ones that simplify. 4th root of 16 is going to simplify. 4th root of V to the 8th is going to simplify. 4th root of Z to the 12th is going to simplify. The 3 and the Z are not. Okay, so let's simplify each of those 3. What is the 4th root of 16? 2. Remember, it's not a square root, it's a 4th root. What is the 4th root of V to the 8th? V to the 2nd. And then 4th root of Z to the 12th. Z to the 3rd. But then we have some things that don't simplify. They're left inside of a 4th root, but we can combine them together. We have that 3 and that Z. And there we go. Okay, number 9. I'm going to switch colors again. I think of number 9 and maybe number 12 as the more difficult ones on here. Let me zoom in a bit. It's the denominator that's the problem. I don't really care about the numerator, but when we simplify, denominators can't have roots in them. And so, because of that, it's helpful to think of that 9 as 3 squared. Since it's a 4th root, notice that your index is 4. It's a 4th root, I need 4 of everything in the denominator. So if I think of 9 as 3 squared, then I have 2 3s. That's closer to having 4 of them than it is to having 1 9. I'd rather have 2 3s than have 1 9. It's just closer to having 4 of something. So I get to multiply in everything that I still need, everything that I'm missing. It's going to be a 4th root again. But if I have 3 squared, how many more 3s do I need? I'm trying to get 4. I need 2 more. And then look at A's. I had 3 A's in the bottom, so how many more do I need? 1. That's what I'm going to multiply in. I'll have to do it to the numerator as well, but let's focus on the denominator just a little bit longer before I worry about the numerator. Let's think about what happens when I multiply that in. So I'll have now 4 3's, and I'll have 4 A's. That was the goal. Why? What happens if I have the 4th root of each of those? It just becomes 3A. There will be no radical anymore. That was the goal. Okay, so the denominator is fixed, but now we have to do the same thing to the numerator. Do I need to write 3 squared when I do it on the top? It helped me on the bottom because I knew I was going to be able to simplify. I'm not going to be able to simplify this time. So I'm going to write it, same value, 3 squared is 9. I'm just going to write it as a 9 because I'm not going to be able to simplify. And since I'm multiplying it by an 8, I would rather think of it as 9 times 8 than I would like to think of it as 3 squared times 8. I think that's just a little bit easier. At least that's how I feel personally. So 9 times 8 is 72. So I get 72A in the 4th root. Can that simplify? Well, remember, 72 is a big number, but think about where 72 came from. 72 came from 9 times 8. 9 we knew was 3 squared. 8, if I broke that down, that's 2 to the 3rd. I have 3 2's, I have 2 3's. Do I have 4 of anything? No, so nothing gets pulled out. That was just our answer. Okay. Number 10. It's like really three problems in one. We have 8 squared of 40. We need to simplify that. We have negative 6 squared of 75. We need to simplify that. We have 7 squared of 80. We need to simplify that. Fortunately, there's square roots. So let's do the first one. We already have the 8 out front. 48 can be broken into 16 times 3. Square root of 16 is, oops, I don't know why I wrote a square root, sorry. Square root of 16 is 4. Square root of 3 does not simplify, so in total, because there was an 8 out front already, there are 32 square roots of 3. Minus. Now the next problem. I would think of 75 as 25 times 3. Square root of 25 is 5. So in total, 30 square roots of 3. Plus, in the next one, 80 is 16 times 5. So I have 7 times 4 times the square root of 5. That's 28 square roots of 5. Now that I've simplified those, we have to see if any of them can combine. Look at the square root parts. Square root of 3, a square root of 3, and a square root of 5. The square roots of 3 can simplify. So 32 square roots of 3 minus 30 square roots of 3 is 2 square roots of 3. And then I still have that 28 square roots of 5. Doesn't simplify with square root of 3. That's just my answer. Number 11, we have to FOIL. Let's do the first part. Square root of 5 times square root of 5 is just 5. Or you could have thought of it as square root of 25. That becomes 5. Then 5 times square root of 2. Sorry, square root of 5 times square root of 2 is square root of 10. Then I distribute the negative square root of 6. Negative square root of 6 times negative square root of 5 is negative square root of 30. Then negative square root of 6 times positive square root of 2 is negative square root of 12. Can any of those simplify? The square root of 12 can simplify because I can divide it by a 4. Oops, that was a really nice square root sign. Let's try that again. Okay, so I can break the 12 apart, like 4 and 3. 10, it's just 2 and 5, nothing I can do there. 30, I can go to 6 and 5. There's no perfect squares. So those two don't break down. So I end up with, on the last one, the square root of 12 becomes 2 square roots of 3. None of those are like radicals. I cannot combine any of them. That is my answer. Well, another fraction problem. Anybody remember the word of the thing that we multiply the denominator by? Conjugate. Conjugate. Square root of 5 plus 2. You do the exact same thing as the denominator, except you change the sign in the middle. And that's the same thing you use in the top. In the top, looks like we just get to distribute. Square root of 15 first plus. Now square root of 3 times 2. The 2 is not in a square root, so they don't make a 6. You just keep the 2 out front and then square root of 3. Then in the denominator, we get a FOIL. Square root of 5 times square root of 5 is 5. Square root of 5 times 2, that's 2 square roots of 5. Positive. Then distribute the negative 2. Negative 2 times square root of 5 is negative 2 square roots of 5. And then negative 2 times positive 2 is negative 4. Notice, here's why we use the conjugate. Look what happens in the denominator. 2 squared of 5, negative 2 squared of 5, they cancel each other out. So in our denominator, all we have left is 5 minus 4, which is 1. So I have a denominator of 1. If we have a denominator of 1, we don't even need to write the denominator. So I have the numerator. Neither of those simplify, and I can't combine. It's all over 1, so I don't even write the fraction. There's your answer. And then we get into the equations, solving. Isolate the radical. So we have to subtract 6. Okay, after I've isolated the radical, how do I get rid of the radical? And this one happens to be a cube root. You cube both of them. That green shows up really nicely, doesn't it? Sorry about that. Cube them both. We get just x minus 4 on the left side. On the right side, 3 cubed is 27. So add 4 to both sides. Get that x is equal to 31. You should check our answers. Sometimes you get an answer that doesn't work. If you plug 31 into the cube root, 31 minus 4 is 27, and the cube root of 27 is 3. So why we get 6 plus 3, that does equal 9, so it works. 14. Here we have a square root, a single square root on both sides. You can square both sides right away. So then you get 2x minus 5 is equal to x minus 1. There's no foiling I had to do on that problem, which is nice. You can expect on the test it'll be one similar to this. You probably won't have to do a FOIL one for this problem. You did on your worksheets, but not on, you probably won't have to do it on the test. It'll be something more like this. Okay, subtract x from both sides. Add 5 to both sides. X is equal to 4. Plug it in to the original to make sure it works. If you plug in 4 to the first square root, 2 times 4 is 8, and 8 minus 5 is 3. So you'd have square root of 3 on the left side. On the right side, plug in 4, 4 minus 1 is 3. You'd have a square root of 3 there also. Square root of 3 equals square root of 3. Yes, it does. So it works out. Number 15, subtract that 2 away first. Okay, this time it's written as an exponent, a fractional exponent instead of a radical. But that's perfectly fine. It's a 1/3. What do we have to do to get rid of that 1/3? Do what on both sides? We don't cube root. It is a cube root right now. Yeah, right now 1/3 means cube root. So to get rid of a cube root, I would cube it. So if it's a fraction, you can think of it as the reciprocal, really. So you take it to the third, because you would multiply those exponents. 1/3 times 3 becomes 1. They cancel each other out. Negative 5 to the third is negative 125. Now solve that. So we get negative 20. If you plug it in, 6 times negative 20 is negative 120. Minus 5 is negative 125. You can do the cube root of negative 125. It's negative 5 plus 2 is negative 3. It does, in fact, work. And then the inequalities. Number 16. Subtract the 4. And we'll need to go and square both sides to get rid of the square root. 881. So we get on the right side, subtract your 5. And get an answer that z is less than 76. Now on the equation problems, I would just go and plug the number in and try it. But this is a whole set of numbers, not just a single number. It doesn't say z equals 76. It says z is less than or equal to 76. So it could be 76, it could be 75, 74, 73. Oh, it could be all of the decimals in between. Oh, and all the square roots in between, and everything all the way down to negative infinity. It's not physically possible to check all of those numbers. So we don't plug it in, but we do instead think about the domain of this problem. The problem's going to come right there because of the square root. What do we know about that radicand z plus 5? If we want the problem to work, z plus 5 has to be greater than or equal to 0. It can't not be negative. If you get negative, we get an imaginary number, and we're looking for real numbers. So I know that radicand has to be greater than or equal to 0. Always greater than or equal to, because it's always got to be bigger. It can't be negative. So solve this to find out what has to be true about z at all times. You know, if this is going to work, the z has to be greater than or equal to negative 5. So now compare this solution set down here. This is what's important. Like that's where the solutions are found. But do they all fit in the domain, or do we have to throw out some of the numbers? So we're looking at all the numbers less than or equal to 76. Do all of them, all the numbers less than or equal to 76, are they greater than or equal to negative 5? I don't think so. We think about a number line. Negative 5 is down here. 76 is up here. We said they have to be greater than or equal to negative 5, but now we're saying, hey, it's got to be less than or equal to 76. So where are the solutions located? Only in between the two. So I have to say negative 5 is less than or equal to z is less than or equal to 76. That doesn't happen on every problem. Number 17, for example, works out nicely. You don't have to eliminate anything. You do have a negative. You have to divide by a negative 1. Since it's an inequality and we're dividing by a negative 1, it does switch the inequality sign, so it becomes greater than or equal to. That's how I know it's going to work out nicely. I will post this video to Canvas. We knew that c plus 4 had to be greater than or equal to 0. C had to be greater than or equal to negative 4, rather. Everything greater than or equal to 5 is greater than or equal to 4, so it works. We don't have to restrict the answer. There it is.